Hello and welcome back. In the last video I demonstrated some file system access code reading off the SD card, and at the very end of that I showed the code loading a program off the SD and executing it. And obviously that opens a door for turning the monitor into something that's a bit more like a primitive operating system. I got quite excited about that, to be honest. I've been spending the time since then writing quite a lot of code to do just that. Let's have a look at what I've done. Now, when I say operating system, I don't mean a modern multitasking operating system. I of course mean something more like MS-DOS in its early incarnations, or perhaps CP/M. Let's talk about the features it would be good to have. I definitely want executable files of some kind. I need to be able to load them. I need to be able to pass them arguments. And I'd quite like to be able to have some kind of search path. And that would allow you to explore the drive and still access a common set of utilities from a common binaries location. And obviously I'd want to develop a number of utilities, otherwise there's not a lot of purpose in putting the effort into building the rest of it out. I'd want my basic operating system to have some system functions. On a PC you have a choice between some functions that exist in the BIOS and also system functions that are exposed by MS-DOS itself to any programs it's executing. And this reduces the amount of work the programs have to do, reduces their memory load, and also allows for some common functionality that always works even if the target of that functionality is changing. So for example, I could have text output functions which might be outputting to the console over the UART, but might be outputting directly to the VGA display, and the programs wouldn't have to know if they went through string output functions that were exposed by the operating system. And for that to work, I'd need a consistent way to call them. I can't just record the addresses of functions within the monitor, because those addresses will change if I have a need to modify the monitor more in future. One nice to have would be booting from the SD card itself. I was actually discussing this with some people on the channel's Discord, and this seemed very important to some people, and I'm kind of sold on the idea. It would be convenient to be able to update the operating system just by writing files to the SD card and not having to get the ROM programmer out. That change alone would feel like a big step towards this being a basic computing platform in its own right. So it's probably worth mentioning the challenges this will present, and the biggest one is how to make this fit. Now, when I've sketched out the memory plan for this system, I've put aside the top 8 kilobytes for the monitor program and the user stack. The monitor program without file system support is just under 7 kilobytes, so there really isn't very much room. So I'm going to have to make some savings in order to add the functionality I'd like to have. Let's start off with a quick look at the current monitor program. Now, I had a number of commands in here, but I also had an undocumented command, and that was kind of making fun of myself. When sitting down at any console, a very natural thing to type in is dir. That's the command on many systems to get a file directory up. And so I added this dummy command in to make fun of myself when I do that. As I've been adding functionality to this system, I have added a number of commands to this monitor to make use of it. There's a disassembler and a memory viewer, but there's also a number of commands for handling the VGA device, the GPIO, and quite importantly actually an audio reset function. So if I'm writing code that accesses the audio system and it crashes, I can quickly suppress any output rather than getting kind of loud constant tones out. So let's switch to my new code. So now the big difference, I can type dir and get a listing of files. Now the part in the middle of this is based heavily on the code I demonstrated in the file system video, but I have added this header and this footer, both of which are very much designed after the equivalent sections in MS-DOS. The serial number is just data that's present in the boot sector. The volume name is a special entry in the root directory. I have had to add the definition of a current directory to the system. And then in the footer, I'm counting files directories, the total size of all the files. And I've also added the total number of bytes free. If you watch carefully, you'll see there's a pause there before it displays the number of bytes free. And this immediately reminded me of early DOS systems I used, which exhibited a similar pause. A couple of people on Discord were kind enough to send me some footage to demonstrate that to you. This viewer, Tom Story, sent me a video of his XT class PC, and that's got a very prominent weight before it shows the total size on this hard drive. And a Discord user by the name of VCS Master sent me this video of his Pentium machine creating a directory on a floppy disk, which shows a shorter pause, but he's reading from a floppy drive, which is a clue about what's going on. In the file system video, we talked about the way clusters are allocated in the file allocation table, and in this example, all the empty grey boxes are unused clusters. And the only way we have to determine the free space in the volume is to go through the entire file allocation table and count the number of clusters that are marked as available. And in a FAT16 volume, we store 256 entries per sector, and that could mean anything up to 256 sectors have to be read in from the disk to find the total amount of space free. That floppy drive, however, is most likely a FAT12 volume. And so not only is the maximum number of clusters smaller at 4084, each of those is only 12 bits, so we fit more of those into a sector. So the floppy drives can return their size quite a bit quicker because there's less sectors to read in and check. So I added a function that can count the total number of free clusters, and that has to eventually sit there in a loop just counting any clusters that are flagged as free in each of the file allocation table entries. I do have this utility called DiskInfo, which outputs all the basic information about the drive. This particular SD card has 4 kilobyte clusters, so each of the file allocation tables is 120 sectors I need to read in. I could potentially cache the number of unallocated clusters and update that whenever I change the file allocation table, but that's not something I've taken the time to do just yet. Obviously, dir is a very common command that you would have expected to see. I've also got cd for change directory. You see the prompt updates, and when I do a directory in here, the header updates to reflect the current directory. You'll notice my executable files have the extension .com. This is the same as the most basic kind of executable files in MS-DOS, and that's because they work in a very similar way. There is no complexity to the format. The operating system just loads them in at the start of memory and transfers execution to the first byte of the program. So for many programs, they don't need to be any different than the data I would stick on a ROM if they were going to be standalone. In fact, the program I last executed will still be present at the beginning of memory. So I could execute it with the jump command from the monitor. I can use the memory dump command to take a look at the data of it. Or I could use the disassembler to take a look at the code directly. So the way this works is quite simple. This is the function inside my monitor program which processes commands. I still might work my way through the same command list I've shown before, but instead of outputting an error at the end, I transfer execution to command execute. And that uses the functions I showed in the previous video to initiate a search of the current directory in order to see if there's an executable file whose name matches the command followed by com. Now it does use 2 bits of information that I haven't mentioned before. So I've got dir current, which is a 16-bit number identifying the cluster of the current directory. And that's all I actually need to store to identify a directory. And I mentioned I wanted something like a path. So the second thing I do, if I don't find a program, is I search a second directory identified by bin path. And I just set that during initialization of the file system if I find a directory called bin in the root of the volume. Now that handles simple programs, but I also want to be able to pass arguments or parameters to the programs. So I needed to define a standard for how the arguments would be passed from the operating environment to the program it was executing. So this is a utility I wrote to test that functionality and debug it. And the work that I already did in the monitor to pull apart the individual parameters being passed to an executable, I just retasked to this purpose. People who've written console programs in C or C++ will be familiar with the ideas of argc and argv. And in this case, I pass the number of arguments using the register D at the start of execution, and DI points to an array of pointers to the text strings of the arguments themselves, argv. Now that was all quite a lot of code, so it's worth us talking about how I made it fit. And that was quite simple. If we call help in the monitor now, we can see the list of commands is a lot shorter. I've added this command called fsinit. And that's my main function to initialize the SD card and check for a usable FAT16 volume. But a lot of the commands that were previously present I've removed. Most significantly, the font for the VJ circuit, that consumed 768 bytes for the data plus the code needed to load it, so removing that command saved quite a bit. But those additional utilities for accessing the GPIO and the AVA VJ functions, they all added a lot to the system as well. But then we can look at this folder and see I've added that functionality back as commands. The previous VJ functionality I included in the monitor all now exists in a command line utility, which I can add to without worrying about the amount of monitor memory space it's taking up. Same for the GPIO functionality. So set the output latches to F0. We should see data write out masked into the LEDs. Nice. So adding the functionality in this way is a lot more flexible. I never added it to the monitor, but I did create a command line utility for outputting the time and date from the RTC chip. And that's actually been holding very good time since I transferred that circuit to the PCB. And that utility actually has command line options to set the date and the time, so I don't need to write custom code to try and initialize that anymore. So if you were watching closely, you'll notice that dir and cd exist as executables in my bin directory. So as well as removing everything that I didn't need to have in the monitor anymore, any new commands I can also just add as executables. So when I showed you the executable code in the monitor, that was accessing this variable dir current. And apart from the initialization function setting that to 0, the cd command is the only thing that needs to update that. It also updates this static string that contains the current path, and that allows the system to display the fully qualified path of the current directory without needing the complicated code necessary to actually decode the entire file system. And the search path for binary utilities is once again just updated by the initialize code. Setting that does need the find file code, but I already had that in the system for implementing the basic executable files. Now another well-known utility I have is type. Now this does take a command line option. So I can take a quick look at test.txt. And this is a flashback to the very first piece of data reading I did off an SD card, but we can just do it natively now with the type command. This text file contains all my current patrons and supporters at the time of creation. Now I actually planned to display the names of my patrons and supporters on the console before now, but by the time I had the functionality necessary to do that, I did hit a small flaw. Some people have characters in their name which are Unicode and don't reproduce very well in the serial terminal. So apologies to those people. One thing I really like about this is I'm going to slowly collect up all of my demos and turn them into executable files so I can just navigate around the system and run them in quick succession. So I converted a few over already. So the Fibonacci sequence was one of the first demos I ever made for the system. The prime number finding code that uses the sieve of Eratosthenes. That's a bit more interesting in its own right. And for those who are aware of the in-joke with Usagi Electric, I've got my Helord program. Now if you look closely you can see that's just 25 bytes. And of course I can disassemble that and see all it's doing is loading a couple of constants in and making a jump into this address E006. So the first few instructions are setting SI to this address where I've got the string, but then this jump is into a system service. Let's talk about how I did that. So here's the source code to that demo. Rather than calling UART write string, I'm calling OS write string. And if I look at my system code, I've got this table at the start, which are just a series of jump instructions. So here we can see OS write string, and that's just the address of a function whose only content is a jump to UART write string. Now each of these jumps encodes into 6 bytes, so I can just create a table at the start of my monitor which is exposing these functions to whatever executables I create. And that means I can both make those executable files smaller, in that case 25 bytes in size, but it also means that the actual code being called at that point is dependent on the operating system itself, so I can change the functionality in one place and then have all my command line utilities adapt to that automatically, at least the ones where I've used these functions. So see, I've added this export symbol directive into my assembler, and that automatically creates an include file which just has the addresses of those jump table entries. So then my executable files can just pull in that include file and they've got access to all the functionality I've exposed in the monitor. It's probably worth mentioning error handling. If I remove the SD card and try and run a program, I'll get an error, but I also update the prompt to reflect the fact that I don't have a valid SD card anymore. But the inbuilt commands in the monitor will continue to work. In fact, if I've got a program loaded at address 0, I can still execute it okay. And if I put the SD card back in, I might be swapping them or perhaps sticking it into my PC to add some new files. But then I can call fsinit and be back to using it immediately. And the final thing to mention is boot.bin. Now that's actually the system itself. I've previously showed the stub loader, which is what I put onto the ROM chip. Now this was the previous code. It contains a binary copy of the monitor, but at the wrong location. I memcopy it up to E000, also load that nice VGA copy of the logo, which you see at startup when the VGA device is installed, and then I jump to that address. And in this case, what I've added is this code. I attempt to initialize the file system, and if that works, I search for boot.bin, and if that's present, I load that instead and bypass the embedded copy. If I reboot the device without an SD card present, you'll see it's actually just loading into that older copy of the monitor with all the extra commands but no file system support. Now I've started work on a graphical version of Snake, but I still have the console version. So now I can get at it easily. I've got even less excuse for not actually being very good at it. Well, I hope you found that interesting. I'm actually finding this whole process to be really rewarding. I can sit down at the system now and do quite a wide variety of things, including showing a lot of the demo code I've written without having to do any of that custom assembly work or loading programs up over the UART. It's really made the whole system feel a lot more like a complete computer. If you join the Toolchain channel on the Discord, link in the description, you can download a copy of the assembler and my emulator so you can have a play around with some of these tools. Maybe see if you can beat my score on SNEC. As always, a big thank you to my patrons and all my supporters. I'm really enjoying this phase of development at the moment and I hope you're finding it interesting as well. I'll see you again soon. Goodbye.